So we have f of x is equal to 3x squared minus 18x minus 81 over 6x squared minus 54. Now what I want to do in this video is find the equations for the horizontal and vertical asymptotes. And I encourage you to pause the video right now and try to work it out on your own before I try to work through it. So I'm assuming you've had a go at it. So let's think about each of them. So let's first think about the horizontal asymptote. Horizontal asymptote. See if there at least is one. So the horizontal asymptote is really what is the line, the horizontal line, that f of x approaches as the absolute value of x approaches infinity. Or you could say, what does f of x approach as x approaches infinity? And what does f of x approach as x approaches negative infinity? So there's a couple of ways you could think about it. Let me just rewrite the definition of f of x right over here. So it's 3x squared minus 18x minus 81, all of that over 6x squared minus 54. Now there's two ways you could think about it. One, you could say, okay, as the absolute value of x becomes larger and larger and larger, the highest degree terms in the numerator and the denominator are going to dominate. The numerator and the denominator are going to dominate. And so what are the highest degree terms? Well, in the numerator you have 3x squared, and in the denominator you have 6x squared. So as the absolute value of x approaches infinity, these two terms are going to dominate. F of x is going to become approximately 3x squared over 6x squared. These other terms are going to matter less. Obviously, minus 54 isn't going to grow at all, and minus 18x is going to grow much slower than the 3x squared. The highest degree terms are going to be what dominates. And if we look at just those terms, then you could think of simplifying it in this way. So that's f of x is going to get closer and closer to 3/6 or 1/2. So you could say that there's a horizontal asymptote at y is equal to 1/2. Another way we could have thought about this, if you don't like this whole little bit of hand-wavy argument that these two terms dominate, is that we can divide the numerator and the denominator by the highest degree, or x raised to the highest power in the numerator and the denominator. So the highest degree term is x squared in the numerator, so let's divide the numerator and the denominator, or I guess you could say the highest degree term in the numerator and the denominator is x squared, so let's divide both the numerator and denominator by that. So if you multiply the numerator times 1 over x squared and the denominator times 1 over x squared, notice we're not changing the value of the entire expression. We're just multiplying it times 1 if we assume x does not equal 0. And so we get to, so in our numerator, let's see, 3x squared divided by x squared is going to be 3 minus 18 over x minus 81 over x squared, and then all of that over 6x squared times 1 over x squared, that's just going to be 6, and then minus 54 over x squared. So what's going to happen? If you want to think in terms of, if you want to think of limits as something approaches infinity, so if you want to say the limit as x approaches infinity here, what's going to happen? Well, this, and that are going to approach 0, so you're going to approach 3/6 or 1/2. Now, if you said as x approaches negative infinity, it would be the same thing. This, and this approach 0, and once again, you approach 1/2. So that's the horizontal asymptote. Y is equal to 1/2. Now let's think about the vertical asymptotes. So let me write that down right over here. And let me scroll over a little bit. So vertical asymptote, or possibly asymptotes. Vertical, maybe there is more than one. Now it might be very tempting to say, okay, you hit a vertical asymptote whenever the denominator equals 0, which would make this rational expression undefined. And as we'll see for this case, that is not exactly right. just making the denominator equal to 0 by itself will not make a vertical asymptote. It will definitely be a place where the function is undefined, but by itself it does not make a vertical asymptote. So let's just think about this denominator right over here. So we can factor it out. Actually, let's factor out the numerator and the denominator. So we can rewrite this as f of x is equal to, the numerator is clearly every term is divisible by 3. So let's factor out a 3. It's going to be 3 times x squared minus 6x minus 27. All of that over the denominator, each term is divisible by 6. 6 times x squared minus 9. And let's see, we can factor the numerators and denominators out further. So this is going to be f of x is equal to 3 times, let's see, two numbers, their product is negative 27, their sum is negative 6. Negative 9 and 3 seem to work. So you could have x minus 9 times x plus 3, just factor the numerator, over the denominator. This is the difference of squares right over here. So this would be x minus 3 times x plus 3. So when does the denominator equal 0? So the denominator equals 0 when x is equal to positive 3 or x is equal to negative 3. Now, I encourage you to pause this video for a second. Think about, are both of these vertical asymptotes? Well, you might realize that the numerator also equals 0 when x is equal to negative 3. So what we can do is actually simplify this a little bit, and then it becomes a little bit clearer where our vertical asymptotes are. So we could say that f of x, we could essentially divide the numerator and denominator by x plus 3. And we just have to keep, if we want the function to be identical, we have to keep the caveat that the function itself is not defined when x is equal to negative 3. That definitely did make us divide by 0, so we have to remember that. But that will simplify the expression. So this exact same function is going to be, if we divide the numerator and denominator by x plus 3, it's going to be 3 times x minus 9 over 6 times x minus 3 for x does not equal negative 3. Notice, this is an identical definition to our original function. And I have to put this qualifier right over here, for x does not equal negative 3, because our original function is undefined at x equals negative 3. X equals negative 3 is not a part of the domain of our original function. And so if we take it out, like if we take x plus 3 out of the numerator and denominator, we have to remember that. If we just put this right over here, this wouldn't be the same function, because this without the qualifier is defined for x equals negative 3. But we want to have the exact same function. So you'd actually have a point discontinuity right over here. And now we could think about the vertical asymptotes. Now the vertical asymptote is going to be a point that makes the denominator equal 0, but not the numerator equal to 0. X equals negative 3 made both equal 0. So our vertical asymptote, I'll do this in green just to switch, or blue. Our vertical asymptote is going to be at x is equal to positive 3. That's what made the denominator equal 0, but not the numerator. So let me write that. The vertical asymptote is x is equal to 3. And so using these 2 points of information, or I guess what we just figured out, you can start to attempt to sketch the graph. This by itself is not going to be enough. You might want to also plot a few points to see what happens, I guess, around the asymptotes as we approach the 2 different asymptotes. But if we were to look at a graph, actually let's just do it for fun here, just to complete the picture for ourselves. The function is going to look something like this. It's going to look something like this, and I'm not doing it at scale. So if that's 1, and this is 1/2 right over here, y equals 1/2 is the horizontal asymptote. Y equals 1/2 is a horizontal asymptote. Y is equal to 1/2. And we have a vertical asymptote at x is equal to positive 3. So we have 1, 2, I want to do that in blue. 1, 2, 3. Once again, I didn't draw it to scale, or the x and y's aren't on the same scale. But we have a vertical asymptote just like that. But just looking at this, we don't know exactly what the function looks like. It could look like something like this. And maybe it does something like that, or it could do something like that, or it could do something like that, or something like that, and that. So hopefully you get the idea here. And to figure out what it does, you would actually want to try out some points. And the other thing we want to be clear is that the function is also not defined at x is equal to negative 3. So if this is, so let me make x equals negative 3 here. So x equals negative 3. So 1, 2, 3. So the function might look, and once again, I haven't tried out the points, it could look something like this. It could look something where we're not, where we're not defined at negative 3. We're not defined at negative 3. And then it goes something like this, and maybe it does something like that, or maybe it does something like that. It's not defined at negative 3, and this will be an asymptote right now, so it'll get closer and closer, and it could go something like that, or it would go something like that. And once again, to decide which of these it is, you would actually want to try out a few values. So I encourage you to after this video, try that out on yourself and try to figure out what the actual graph of this looks like.